Chapter 21, Analysis of Variance. The independent samples t-test examines whether a difference between two means is statistically significant. Analysis of variance expands upon the t-test. It can examine whether differences between two or more sample means are statistically significant, which is to say, not likely to be due to chance. ANOVA, as it is known, is most often used with three or more means. When there are only two means, more researchers probably tend to go with the independent samples t-test. The hypothesis pair in ANOVA is always non-directional. The null states that population means are equal, that is, the means of the populations from which random samples are selected are equal. The alternative states that those means are not equal. ANOVA generates two estimates of the population variance. These are the mean square within and the mean square between. Now, the mean square within is based on differences within group. That is to say, it's based on within any given group how variable are scores of the different cases in that group. The mean square between is based on differences between groups. In other words, it's based on how much do the sample means differ in the different groups. For greater depth on the theory behind the mean square within and the mean square between, and on calculations, consult the text. When the null is true, which is to say when population means are equal, we expect the mean square within and the mean square between to have similar values. When the null is true, only chance, the luck of the draw, causes the mean square between and the mean square within to differ. Now, when the null is false, population means differ. Because population means actually do differ from one another, sample means differ more than would be expected just by chance. In other words, the real difference in population means causes the sample means to spread out more than one would expect just by chance alone. Now, the MSB is based on differences between sample means. So as the sample means spread out more, the mean square between becomes larger. Now, the spreading out of the sample means doesn't affect the spread of the values within any given sample. So the spreading out of the sample means doesn't affect the MSW at all. In sum, when the null is false, we expect the mean square between to be larger than the mean square within. Now, ANOVA is based on the F distribution, or more specifically the F ratio. And we obtain an F ratio when we divide one estimate of population variance by another. So in ANOVA, one obtains F by dividing the mean square between by the mean square within. And here is that formula. When the null is true, we expect the mean square between and the mean square within to have similar values. Their values differ only due to sampling error. Thus, when the null is true, we expect the value of F to be reasonably close to 1. When the null is false, we expect the mean square between to be larger than the mean square within, and thus we expect the value of F to be greater than 1. At some point, and this differs in different situations, the value of f becomes sufficiently greater than 1 that we reject the null of equal population means. Well, as mentioned, ANOVA is based on the f distribution. Just as are the chi-square distribution and the t distribution, the f distribution is a family of distributions. So the characteristics and shape of different f distributions vary according to degrees of freedom. Now there are 2 different degrees of freedom that define each f distribution. So this is different from chi-square and t distribution, where we're only dealing with 1 degree of freedom. But for the f distribution, we have degrees of freedom that are associated with the mean square between, that's the numerator in the formula, and we have degrees of freedom that are associated with the mean square within, the denominator in the formula for f. Degrees of freedom for the mean square between equal j minus 1, where j is the number of groups. So if, for instance, you had 5 groups, you would have 5 minus 1, or 4 degrees of freedom associated with the mean square between. Degrees of freedom for the mean square within are computed by taking the sample size n, that being the full sample size, all persons in all samples in the study, and dividing by a. So suppose, for instance, that you had 3 groups, which is the same as to say you had 3 samples. There were 30 in each group. How many degrees of freedom are there associated with the mean square within? So you would sum 30 plus 30 plus 30. You would have 90 total cases. That would be n. You would subtract j. There are 3 groups, so 90 minus 3 equals 87 degrees of freedom associated with the mean square within. Let me talk about the assumptions for ANOVA. One assumption is the normality assumption, which is that populations are normally distributed. And just as is the t-test, it is robust to this assumption. Here are the situations when it's sufficiently accurate. So ANOVA is robust when n is 10 or greater and no sample has strong skew, and also when n is 20 or greater and no sample has extreme skew, and finally when n is 60 or greater, even when skew is extreme. So in each of these situations you'll get sufficiently accurate results. And the n here is referring to the number in a particular group. Now we talked about the equality of variances assumption for the independent samples t-test. ANOVA also has an equality of variances assumption, which is to say that populations have equal variances, or we can phrase this to say that the random samples have been selected from populations that have equal variances. This assumption is tested with an equality of variances test, and the computer will carry that out for you. Now, when sample sizes in the different groups are equal or very nearly so, ANOVA is robust to the equality of variances assumption. So basically, with equal sample sizes, you don't need to be concerned about this assumption. Or if sample sizes are very, very similar, you don't need to be concerned that that unequal population variances will cause inaccuracy in your results. Now, when sample sizes differ, ANOVA is not robust to the equality of variances assumption. So when this is the case, you use an alternative to ANOVA. One such alternative is Welch's test. and computer software packages can implement these different alternatives for you. The hypothesis pair in ANOVA is non-directional. One can express the null in symbols. So here is the null expressed in symbols. And so you can see the null is that all populations have equal means. So mu is symbolizing the mean in each population. So this mu with the 3 next to it is symbolizing the mean in the population from which group 3 has been randomly selected. The null then states that all population means are equal. The alternative states that population means differ. ANOVA is a one-tailed test with a rejection region in the upper tail. So in this regard, it's like the chi-square tests, and it's an exception to the general rule that non-directional pairs go with two-tailed tests. The decision rule for ANOVA is to fail to reject the null when the obtained f is less than the value of f in the f distribution table. You reject the null when the obtained f, that is the f that you calculate, is greater than the f in the table. And the critical values of f, the values of f that will result in rejection, differ for different f distributions. They differ for differing degrees of freedom. So we'll make use of our family ethnicity data again in the adoption sample. Our dependent variable in our example is the score on a behavior problems instrument. Parents filled out an instrument and basically checked whether kids had a given problem, and score on the instrument is very close to the number of problems checked. Where problems were particularly severe, parents could indicate this, and that was also taken into account in the behavior problems measure. This top table lists some descriptive data. We have 696 cases. The largest group is the white inracial group. Let's look at the mean scores. The white inracial group has the highest mean behavior problem score. The lowest score is in the minority inracial group, and the transracial group is in between. Here are the standard deviations in the three groups, and you might note that these standard deviations are quite similar in each of the groups. Now, looking at the descriptive data here at the in this table, the sample means do indeed differ, and thus the variables are related in our study sample, and we've got to determine whether these differences in means are large enough so that they're unlikely to be due to chance alone. And I'll mention that all of these sample sizes are large, so we don't need to be concerned about issues of skewness. If we had smaller samples, we'd have to be sure that we didn't have very strong or extreme skew in one of the samples. That is to say, if the samples were much smaller than were these. So one of the first things that statistical software packages do, and we're going to carry out ANOVA by a statistical software package, is they compute a test of homogeneity of variances, which is the same thing as equality of variances. So the SPSS statistical package conducts a Levene statistic on determining whether the equality of variances assumption is differed. So SIG stands for p-value. The p here is 0.793. That p is much greater than 0.05. That's presumably the level of p that we would use, so we would fail to reject the equality of variances assumption. So there's no indication that population variances differ, and we can confidently carry out ANOVA rather than an alternative. And you see the p-value is quite high, I mean reasonably close to 1, and just do eyeball how similar these standard deviations are. I mean, standard deviation is the square root of variance, so you can just simply eyeball these standard deviations and see that they're quite similar, and so it should make intuitive sense that we're not rejecting the null of equal variances, which is in essence the same thing as the null of equal standard deviations. Well, the table at the top of this slide is termed an ANOVA table. And let's see where some of the different terms on the ANOVA table come from. Here's degrees of freedom for the mean square between, and it equals j minus 1, 3 groups minus 1, 2 degrees of freedom. Where do the 693 degrees of freedom come from for the mean square within? We have a sample size of 696. We have 3 groups, so 696 minus 3 gives us our 693 degrees of freedom connected with the mean square within. Now I haven't mentioned sum of squares yet, and this text simply defines sum of squares as being used in calculating the mean square. So I don't per se demonstrate how to calculate these, but do observe that the mean square comes from dividing the sum of squares by the degrees of freedom. So the sum of squares associated with the mean square between, which is to say the between group sum of squares divided by the between groups degrees of freedom, gives us 5824.2, and that is the mean square between. That is our estimate of the population variance based on the differences in means between the groups. So here is the sum of squares between, and we divide this quantity by 693, the degrees of freedom associated with the mean square between, and that yields, and I mean to say the mean square within. To calculate f, we divide the mean square between by the mean square within. So 5824 divided by 680.5 yields an f of 8.559. SPSS uses the term SIG to stand for P, that is the probability associated with the test, and the probability that it yields is 0.000. Let's go ahead and presume that we were using the 0.01 level. I'm not sure that we actually specified that, but the probability associated with the test is less than our selected significance level. Therefore, we reject the null. And indeed, in this situation, the difference between the sample means is highly unlikely to be due to chance alone. Now, if we did not have access to a statistical software package, and indeed in some of the problems that you'll be doing in Rosenthal's course, you'd use the table of critical values of the F distribution that's found at the back of the text. So what you need to do is locate the appropriate tabled F value according to degrees of freedom for the MSB and also for the MSW and for the selected alpha level. So we had 2 degrees of freedom for the mean square between. So this is the column that we'll use for mean square between. Now oftentimes for the degrees of freedom for the mean square within, the exact degrees of freedom isn't listed in the F distribution table. So in that situation, you use the closest lower value. So our degrees of freedom were 693, The next lower value in the table is 250. So these are the values that we're going to use. And then finally the table is listing significant values of f both at the 0.05 level and at the 0.01 level. We are using the 0.01 level, and so the tabled value of f, that is the critical value of f, is 4.69. Our decision rule calls for rejection of the null if the obtained value of f equals or exceeds the critical value, that is the value listed in the table. Our obtained f of 8.559 is indeed greater than 4.69. Therefore, we reject the null at the 0.01 level. So when we reject the null in ANOVA, we conclude that all population means are not equal. We don't draw a conclusion about which particular pairs of means might differ significantly. Multiple comparisons discussed in the next video get at this topic.